SN1 reactions, that's going to be the topic in this lesson. Now, in the last lesson, we went through SN2 reactions, and now we're going to do the same with SN1. We're going to go through the mechanism and see how it involves carbocation formation, and then we're going to look at a variety of factors that affect the outcome of an SN1 reaction. We'll look at substrate effects, nucleophile effects, solvent effects, and leaving group effects. Same thing we did for SN2 in the last lesson. And then finally, in the next lesson, we'll actually compare and contrast SN1 and SN2 and show how you can predict the products of any given substitution reaction. Now, if this is your first time joining me, my name is Chad, and welcome to Chad's Prep, where my goal is to make science both understandable and even enjoyable. Now, this is part of my brand new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year, so if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I post a new lesson. All right, so now let's take a look at SN1 reactions. And just like with an SN2 reaction, the first thing I wanted to come to your mind was backside attack. With an SN1 reaction, we'll find out that the major and most important intermediate in the reaction is a carbocation. And so the first thing I want to come to your mind for an SN1 reaction is carbocation. So in fact, I want it to come to your mind so much that I wrote you a horrible song. So when the song goes, SN2 backside attacking you, SN1 carbocation. Yeah, it's horrible. So, and if you're sleeping tonight and you're thinking of that song, I am sorry. And one, you got problems. You probably don't get out too much. Well, in fact, we all don't get out too much right now. So, but that's the song. SN2, backside attacking you. It's all about backside attack. And then SN1, carbocation, because it's going to be all about the carbocation. And again, these things are important because they remind us of the different substrate nucleophile effects that'll be involved in stuff like this. So, SN1, we call it substitution nucleophilic unimolecular. So, and again, whereas SN2 is bimolecular, this is unimolecular. Only one reactant molecule involved in the rate determining step. And it turns out that reactant molecule is going to be the substrate. Only the substrate's involved as a reactant at slow step. And it's first order. So, and that's what the unimolecular means. Only one reactant molecule and a first order rate law. So in this case, if we kind of take a look at that mechanism, it turns out in step one, your leaving group leaves. All on its own. The nucleophile is not involved in this whatsoever. And if that leaving group leaves, that's where our carbocation intermediate comes from. Cool. Carbocation here. So notice that word. It's not a carbocation. It's not like you're taking a vacation from carbohydrates or something like that, like the Atkins diet. So it's carbocation. So, and your carbocation here does not have a filled octet. Positive formal charge, typically highly unstable, so super high energy intermediate. So this first step is going to be very endothermic, big uphill increase in energy. So, and this is going to be the slow step in your reaction, the rate determining step we often say. Cool, and because only our substrate here, in this case 2-bromobutanes involved, that's why he's the only one showing up in the rate law. So if we write the specific rate law in this case, cool, there's your 2-bromobutane. Cool, you double his concentration, the rate doubles. Done. That's all you want to know about this guy here. Now, this gets a little bit tricky here because then who is our nucleophile? Well, that nucleophile here is methanol. Now, it turns out methanol is a weak nucleophile. He does not have a negative charge. He's just an alcohol. A lot of students see this like, hey, Chad, he's got an OH. Chad, look, he's got an OH. He's not a metal hydroxide, which is ionic. And that has a metal hydroxide. Hydroxide's a strong nucleophile. But that's a non-metal. He's bonded to carbon. This is just an alcohol. This thing is about as reactive as water. Water's not a good nucleophile, not a good base. He's not a good nucleophile, not a good base. So in this case, weak nucleophile, but your carbocation is so highly reactive, he doesn't care. He's like, I just need somebody, anybody. So your next step is nucleophilic attack. Cool, and oxygen's going to come and attach to that carbon right there. Cool. Now, one thing you should note is how we attach that carbon's a little bit unique here. So this carbon right now is no longer tetrahedral and sp3 hybridized. Once the bromine leaves, he's now sp2 hybridized. That makes him trigonoplanar and flat. He exists in a single plane here. And so when methanol attacks, he either attacks from the front face or the back face. If he attacks from the front, it would be a wedged bond. And if he attacks from the back, it would be a dashed bond. And so in this case, what I might do, instead of drawing them both out, is I might just make it a squiggly bond. One possible convention. Cool. Now, one big difference here is our nucleophile here was not negatively charged, he's neutral. Notice you look at oxygen here, oxygen's bonded to carbon and to a hydrogen. He's got 2 bonds, and we're used to seeing oxygen have 2 bonds like in water and stuff. So he normally has 2 bonds. Well, all of a sudden now he's got 3 bonds. And when you've got a neutral nucleophile, it ends up having 1 additional bond past what it normally likes to have, if we want to use that. Whereas when you start with a negatively charged nucleophile like we do in most SN2 reactions, it's already short a bond, and making another bond gives it its normal number. So in this case, this thing, you might recognize oxygen with 3 bonds and a positive charge, very analogous to H3O+, which is a strong acid, and this thing's highly acidic as well. And if you get here, as long as you have an H, you're going to let your solvent come and deprotonate, do a proton transfer reaction. So in this case, it turns out methanol is not just the nucleophile, he's also the solvent. And being the solvent, we'll have another molecule come in. Our solution is chock full of solvent molecules, so if I need to use one, I'll just draw it in. And we'll come and deprotonate here. And again, generically called a proton transfer. And now I'll take the time to draw out both versions of this. Cool, so we get, in this case, since this happened at a chiral center, we get both the R and the S forms here, so both enantiomers, if you will. Cool, so that's one big distinguishing factor between SN1 and SN2. With SN2, we only saw inversion. For SN1 here, though, if it happens at a chiral center, we say that racemization takes place, even though we'll find out this is not a true racemic mixture. So, and then also we get one of our solvent molecules protonated as well, though we wouldn't, normally look at him as being a product, although if I'm drawing out the mechanism, I should draw him in. Cool, but if I'm just, drawing organic products, we would just draw these 2. Again, not part of a mechanism, just said if we're just predicting products. Yep, draw these 2. Cool. Now, like I said, this is not a true racemic mixture because it's not exactly 50-50, it turns out. So it turns out we're going to get a slight excess of the inverted product. So in that case, that's this one down here. So a little higher than 50%. And of the retained stereochemistry, we're going to get a little lower than 50%. So it turns out that bromine here is leaving from the wedged position. He's leaving from the front side. He's like, I'm bromine and I'm big, and I'm leaving from the front side. And as he leaves, he blocks the way from methanol attacking from the front side. Now again, methanol, bromine leaving and methanol attacking is 2 different steps. So, and even though they're isolated in time, bromine's still out here in the way a little bit out in front of the molecule, having left from the wedge. And so methanol has a harder time attacking from the front than the back. So, and again, it's, it's not like it's 90-10 or anything like this. So in this case, we don't want to define it anything more than saying a little higher than 50%, a little lower than 50%, but it's not a true racemic mixture. And you should know that the inverted product, there's a slight excess of him. So, but again, we still say that racemization takes place in an SN1 reaction. All right, one other thing to note, another big buzzword. So for a lot of SN1 reactions, it doesn't have to work out this way, but it usually does. So is that your solvent and your nucleophile are one and the same. So, and when your solvent's involved in a reaction as a reactant, your solvent's getting consumed in that reaction, and we will call it a solvolysis reaction. Cool. And so there are a lot of solvolysis reactions that exist. SN1s, a lot of SN1s are just examples of solvolysis, but SN2s typically, and I can't actually think of an exception, are not solvolysis reactions. So if I say the word solvolysis in this context, you think SN1. Now, we'll find out, towards the end of second semester, there's a lot of other reactions that end up using the solvent as part of the reaction that could be termed solvolysis. So I don't want to use this universally, but in this chapter, if I say solvolysis, you should think, oh, that means SN1 reactions in this chapter, not SN2. All right, so another big buzzword to take away here. So if we take a look at some of the substrate effects now, so again, SN1 is all about the carbocation. So in somewhere along the way, you guys learned that tertiary carbocations are more stable than secondary carbocations, are more stable than primary carbocations, are more stable than methyl carbocations. And so as a result, we'll find out that tertiary halides react the fastest, then secondary halides. So, and then finally, primary halides and methyl halides, the carbocations that result from primary methyl halides are usually so unstable that they're just not going to form. And so tertiary halides react the fastest, then secondary, and then primary methyls, we say, don't react in SN1 reactions. Now, there are exceptions. If it's a primary halide and it's allylic, if there's resonance, so potential for the carbocation, well, that would be an exception. So, but that's not kind of part of this normal trend. But so if I gave you something like this, so this is not just primary, although he is primary. So, but he's primary and again, what we call allylic. And if this chlorine were to up and leave, we'd get this resonance stabilized carbocation, and we could draw that other resonance structure. Cool. But outside of any kind of resonance stabilization of your carbocation, tertiaries react the fastest, then secondaries, primary methyls don't react, again, barring some sort of resonance. Cool, but we should keep in mind that resonance can stabilize our carbocations as well. It's not just about most substituted, although that's what it's about most of the time, but resonance stabilization can also play a role for SN1. All right, so now we see this is the exact opposite trend as we saw for SN2. For SN2, which was all about backside attack, we wanted the least amount of steric hindrance possible. And so methyls were the fastest, then primary, then secondary, tertiaries don't react. Now it's tertiaries that react the fastest because we're getting the most stable carbocation, then secondaries, and then primary and methyl halides don't react instead. Cool, and those are our substrate effects. Cool, one other thing you should look at. So if we look at first the energy diagram for this reaction, the one we did right here, and in case you're wondering, RXN is my shorthand for reaction. So we'll plot energy versus reaction progress. We can see that we got 1 step, 2 steps, 3 steps. And so SN1 reactions, again, they don't have a concerted mechanism. So the leaving group leaving and the nucleophile attacking is in 2 different steps. And so you're always going to have more than 1 step. You're going to have at least 2, and in this one we see we have 3, which is pretty common. 3 steps is going to mean 3 hills. So, and in this case, you'll find out that that first step, it's going to have the highest activation energy because we're forming that very high energy carbocation intermediate. That's going to be the slow step. It's going to have the highest activation energy. Cool. And if we kind of take this the rest of the way. And so in this case, again, 3-step reaction gives me 3 hills. And the first step definitely had the highest activation energy out of any of those 3 steps. So, and that would be another way of recognizing its slow step, if you will. So if we look at an energy profile here, it's definitely easy to distinguish SN1 from SN2. SN2 reactions, again, typically have just a single step, concerted mechanism. SN1 reactions are always going to have at least 2 steps, but 3 here is pretty common, with that last proton transfer step being really common for a lot of SN1 reactions. All right, so again, the kinetics are all about forming that carbocation in that first step. And one way we can kind of facilitate this, it turns out, is by adding some silver nitrate into our solution. So we often use silver nitrate to help SN1 reactions happen. And specifically when we have chloride, bromide, or iodide as our leaving group. So it turns out that once bromide leaves here, once we've done that first step, and we get here, so notice he can go forward, but also there's not a huge activation energy to go backward as well. He might decide, I'm just going to go back and reattach. That was a good place to be. So, and in this case, to prevent that, we can add some silver nitrate. And the idea is that silver halides are super insoluble. Silver chloride, silver bromide, silver iodide. And so as soon as bromine leaves, so our silver ions here are going to combine with that bromide and precipitate out. And either we draw, a little S for solid, or oftentimes we'll draw that little down arrow, which means it precipitates and falls out of the solution. So because the bromide's now part of a precipitate that fell out of the solution, this becomes irreversible. And so this helps aid in carbocation formation. So if you see ever, not just methanol or water or something like that, some weak nucleophile we'll find out, but silver nitrate written as well, you should think, oh, they're trying to aid in carbocation formation. We're probably doing SN1 there as well. So just wanted to throw in silver nitrate's not, going to be part of the product or anything like that. It's just there to aid in carbocation formation. Cool, let's also talk about nucleophile effects for just a second. So with SN2, the nucleophile was in the rate law, it was in the rate determining step, and we needed a strong nucleophile. But in SN1 reactions, it's not in our rate law at all. It's not part of the rate determining step. So, and we're going to find out that weak nucleophiles are okay. In fact, most SN1 reactions involve a weak nucleophile. If they involved a strong nucleophile, they'd probably do SN2 instead. So most weak nucleophiles, most SN1 reactions, your weak nucleophile is going to be the case. And the idea is that your carbocation is a super reactive electrophile, super unstable, high energy electrophile. And he's like, I don't need a strong nucleophile. Just any nucleophile will do. Let me bond to a nucleophile. Perfect. Methanol, water, you're ugly. Great, I don't care. That works. So that's kind of the idea here. Weak nucleophiles are okay for SN1 reactions, and that's going to be the case most of the time. So we'll find out that SN2s, we need a strong nucleophile. SN1 reactions, most of the time, are going to involve a weak nucleophile, and that is probably the single biggest determining factor between SN1 and SN2 is the strength of the nucleophile. If you can recognize that you have a strong versus a weak nucleophile, you've probably just figured out whether or not you're doing SN2 versus SN1. Cool. Second after that will be the substrate effects. Notice here, if you've got a tertiary substrate, you're doing SN1, not SN2, because SN2 can't use tertiary substrates. If you've got a primary or methyl substrate, well, then you're probably doing SN2 because you can't use primary methyl substrates in SN1, again, barring any sort of resonance, stabilization of your carbocation. So keep that in mind. One other pesky thing we got to talk about here with these carbocations. So somewhere in the course, you probably already learned that carbocations can undergo rearrangements. This is not something we ever had to worry about with SN2. We don't even have an intermediate in SN2 reactions. So, but for SN1 with a carbocation intermediate, we do sometimes have to worry about carbocation rearrangements. Now, in the example we did up here, we didn't have to worry about it. Our carbocation was secondary. Typically, the rearrangements can only happen to one of the adjacent carbons, and only if the carbocation gets more stable. Well, going from secondary here, I've got an option to go to a primary here or to another secondary here. That's not more stable, and equally stable is not good enough. It has to be a more stable carbocation as it rearranges. So there's no favorable rearrangement here, so it wasn't something we had to worry about. But let's do an example where we do have to worry about rearrangements. All right, so let's take a look at this next reaction here. So we have got a secondary halide on our substrates, or for our substrate anyways. And again, methanol, an alcohol, another weak nucleophile, just like we saw before. We should be predicting SN1. So first thing that's going to happen is your leaving group is going to leave, and we're going to form that carbocation. Cool. And in this case, having a secondary halide as our reactant, we've now formed a secondary carbocation. So a secondary carbocation has two adjacent carbons, these two right here. And the top one here is secondary, but the bottom one is tertiary. And so we do have a favorable rearrangement. We can get a more substituted, more stable carbocation right next door. And we would accomplish that with a hydride shift. And so I'm going to draw in the hydrogen that's going to move over here. That hydrogen, the bond's going to break and reattach over here. That's going to leave what was formerly our carbocation. So having a filled octet now, and now this carbon will be missing a bond and be the carbocation in the subsequent structure. All right, notice I didn't draw the hydrogen on the adjacent carbon or anything like that. We often don't draw hydrogens in unless they're part of the mechanism. So it's there. That guy now is a filled octet. So, but this carbon here is now missing a bond. He's only got 3 bonds. There's no hydrogen there anymore. So, and having only 3 bonds, he's not sp3 hybridized and not tetrahedral. He's now sp2 hybridized and trigonal planar and flat. And that's why I've not drawn this as a wedge, because he's not a wedge. This is now trigonal planar, not tetrahedral. All right, now it's a tertiary carbocation here, and again, most of the time when rearrangements occur for carbocations, typically there's one favorable rearrangement. But there's nothing to say that it can't have more than one successive rearrangements, but it does have to get more stable every step along the way. And so we should just verify that none of the adjacent carbons here would be more stable. So with our tertiary carbocation, it's next to a secondary carbon here, not more stable, next to a secondary carbon here, not more stable, and next to a primary carbon here, not more stable. So we're done with rearrangements. And so now we can kind of see where methanol would ultimately come and attach to get to the major product. All right, so that's where methanol is going to attach. And eventually, again, one of these H's will get deprotonated like we showed in the mechanism before. So that's why I'm kind of drawing 2 arrows here. We're taking 2 steps, combining them to one, not showing the complete mechanism here. Just wanting to get to this final product. So again, all of methanol attached right in that location and then got deprotonated by another methanol molecule. So it takes 2 steps to get to this final product. Now, in this case, where we ultimately attach, that is not a chiral center. So it is bonded to 2 identical groups as you go around the ring. And so since there's no 4 different groups there, that's not a chiral center. And if it's not a chiral center, well, then I don't really care about stereochemistry. Whether I'd show the wedges and dashes, it only exists in one way. So whether I make the CH3 the wedge and the OCH3 the dash, or the OCH3 the wedge and the CH3 the dash, it's the same thing either way. So we don't have to show stereochemistry if it's not a chiral center. So we get a single achiral product in this case. And so the idea that inversion takes place in SN2, whereas racemization takes place in SN1, only if the reaction's occurring at a chiral center will we even notice those things. Cool, so not the case here, but we did go through a carbocation rearrangement, and notice not only did we kind of get a rearrangement of the carbon skeleton here, but it also added an additional step to our mechanism. So in this case, we had our first step was carbocation formation, second step was rearrangement of that carbocation, and then 2 more steps to get to our final product for a total of 4 steps in this one. So if you drew out the energy profile, you'd see 4 hills on the way to your product and stuff like that. So mechanism a little longer when you have a favorable carbocation rearrangement. One other thing to note, it doesn't mean that all product is formed through rearrangement. It just means that your major product is formed through rearrangement. So you might see a little bit of this product. It could be a wedge or a dash in this case. That could have a little bit of that product in your solution. So we're not saying that you get none of it, but if you're asked to predict the major product, you're predicting this guy, not the minor product over here. So just one thing to note. Okay, so we've talked about the substrate effects. The more substituted, the faster for SN1. We've talked about nucleophile effects, where simply just most SN1 reactions are going to involve a weak nucleophile. That's okay. Not involved in the rate law. And now we've got to talk about solvent effects for just a minute as well. So in SN2, we decided that polar protic solvents weren't the greatest thing because they would stabilize the anion nucleophiles, making them weaker nucleophiles. Well, for SN1, we're going to stabilize an ion as well, but the ions we're going to stabilize are the carbocations, and these are not the reactants. These are the intermediates we form in the rate determining step. So for SN2, the ion we stabilize is the reactant in the rate determining step. You stabilize that reactant in the rate determining step, you slow the reaction down. But now we're stabilizing the intermediate, the product of the rate determining step, and if you stabilize that, you speed the reaction up. And so in this case, our ion dipole interactions with polar protic solvents stabilize the carbocation. We're going to form these ion dipole interactions with our carbocation and the leaving group anion. And it turns out without those interactions, these reactions don't go. SN1 reactions have to have polar protic solvents to form those strong ion dipole interactions and stabilize the carbocation. So without polar protic solvents, SN1 reactions don't occur. So there's another distinguishing factor. It's kind of the least important of them. But for SN2 reactions, polar aprotic was strongly preferred. So with bigger nucleophiles, you can get away with using polar protic, but it will still go faster with a polar aprotic solvent. But for SN1, no ifs, ands, or buts. Your solvent has to be polar protic. Can't use polar aprotics at all. And so if your solvent is polar protic, well, it could be SN1 or it could be one of the rare SN2s. Okay, but if your solvent's polar aprotic, well, you can't do SN1 and it has to be SN2. All right, one reminder, your typical polar protic solvents, water, alcohols, and maybe an occasional carboxylic acid, but water and alcohols most of the time. Cool, finally one more thing here and talking about leaving groups. So the leaving group leaves in both SN1 and SN2 reactions. That's the one thing they have in common. In the rate determining step, the leaving group leaves in both. In an SN1 reaction, that's the only thing that happens. In an SN2 reaction, it's one of the 2 things that happens. In an SN2, you have the nucleophile attacking and the leaving group leaving. But in both SN1 and SN2, the leaving group leaves in the rate determining step. And you need a good leaving group in either case. And so the leaving group trend here is exactly the same. So OTS would be better than iodide, iodide would be better than bromide, bromide would be better than chloride, and fluoride would be a bad leaving group again. So we can rank the speed of SN1 reactions. If the only difference is your leaving group, you could use this ranking to figure out who's faster, who's slower as well. Now, if you found this lesson helpful, consider giving me a like and a share. A couple of the best things you can do to support the channel. And if you've got questions, feel free to leave them in the comments section below. Now, if you're looking for the study guide that goes with this, or if you're looking for practice problems on this lesson, check out my premium course on chadsprep.com.